So semua boleh nampak skrin saya? Boleh dengar suara? Boleh
Boleh.
Okay, thank you. So last week we have learned up to chapter 3. So we have stopped up to topics in power calculations. Okay, but we haven't gone through the power calculation yet. So before we continue our class for today, so I would like to refresh again what we have learned so far last week. Okay, so we have learned about amplitude modulations. Okay, so last week we have seen about AM, how the AM waveform is generated by the modulator in the transmitter. Okay, so okay, so maybe I will put here modulator. Okay, so this modulator is part of transmitter. Okay, this modulator is part of transmitter. So the job of the modulator is to do the process of modulations. So part of a transmitter, and this is transmitter. Okay, and then this one goes to the antenna. So here we have a VMT, the input message. And when we do the process of modulation, remember that we need to have at least 2 input signal. Okay, at least 2. So we can have more than 2 actually. Okay. So another one is what we call as the carrier signal, VCT. Okay. So in your syllabus, we use VMT and VCT as a sine wave. Okay, so both VMT and VCT is a sine wave in your syllabus. Okay, so I put just do like this. So VMT is equal to VM sine okay. I hope my computer will not hang again. Kejap. This one is this for example here. Okay, VMT is V sine VM sine 2 pi FMT, while VCT is VC sine 2 pi FCT. Okay, so and we produce output here as what we call as the VAMT. Semua boleh dengar suara saya?
Boleh betul.
Boleh
Okay,
Doktor.
yeah.
Boleh, Doktor.
But my screen is freezing. So saya punya screen dia jadi hang. Selalu macam tu. Kenapa? Okay. So saya cerita je lah sementara saya do something. So we produce a VAMT by mixing both of these signals, okay, together. So the mixing process will change the amplitude property of the carrier in accordance with the amplitude variation of the input message. Okay, so perubahan hasil daripada mixing ini mengakibatkan perubahan amplitude, okay, pada mengakibatkan perubahan amplitude carrier berkadaran dengan perubahan amplitude daripada input message. Okay, so this is what we call as the amplitude modulation. So the amplitude modulation is the process of changing the amplitude property of the carrier in accordance with the amplitude variation of the input message. Okay, so so if you see from the input here, in your syllabus, it used the sine wave. So sometimes if you read from other literature books, it use cosine, cos function. Okay, so it doesn't matter. Okay, so when you want to derive the AM signal, okay, you need to derive from the envelope waveform, okay, which is V in bracket VC plus VMT close bracket multiplied with the sine 2 pi FCT. So that one produce VC sine 2 pi FCT plus VM sine 2 pi FMT sine 2 pi FCT. Okay, and if you rearrange the equation based on the trigonometry identity, you will get the final equations of AM, which is VC sine 2 pi FCT plus Vm over 2 cos 2 pi in bracket Fc minus Fmt minus Vm over 2 cos 2 pi in bracket Fc plus Fmt. So you have the carrier portions, you have the lower sideband portion, and you have the upper sideband portions. And from there, from the equations, then you can draw the frequency spectrum. Okay, so the frequency spectrum can only be drawn based on the equations. Okay, you cannot simply draw the frequency spectrum without the equations. Okay, selepas dapat equation barulah kamu boleh boleh lukis frequency spectrum tersebut. Okay, and the spectrum for AM double sideband full carrier, remember we must have the lower sideband, we have the carrier, and we have the upper sideband. Okay, so the upper sideband and also the lower sideband, the amplitude is Vm over 2, and the amplitude for the carrier is Vc. And remember for the frequency, so the frequency for the carrier located at the Fc, F carrier, and frequency for the lower sideband is located at Fc minus Fm. Frequency for the upper sideband located at Fc plus Fm. Okay, so if you see the bandwidth, the total bandwidth from the highest frequency to the lowest frequency, so Fc plus Fm minus Fc minus Fm, so you get 2 Fm. So the bandwidth for the double sideband full carrier is 2 Fm. Okay, 2 times the fundamental frequency. Sorry, 2 times the input message signal. So in this case, it is the 2 times the highest frequency of the input message. nanti kita akan lihat, later we will see that what if we have more than one frequency input. Okay, nanti kita akan lihat bagaimana sekiranya kita ada lebih daripada satu frekuensi input and we have only one carrier. Okay. Sekejap. Sampai sekarang saya dah cuba pelbagai cara tetapi masih ada problem. I don't know, is it because of the whiteboard or because of the PC or sekejap, sekejap. So maybe I need to do restart. Saya dah cuba pelbagai cara, dah tekan pelbagai button dalam saya punya keyboard ya. So dia still tak boleh nak dia keep on freezing So I click this one, is cannot be done. Sekejap So sekejap. Okay, semua masih ada di situ Pelajar-pelajar semua masih ada? Sekejap. Okay, sorry for the technical issue. Semua boleh dengar, boleh nampak saya punya screen
Boleh betul.
Okay, thank you. So I will continue. Sorry my screen is keep on freezing. I don't know, is it maybe because of this whiteboard software. So sine 2 pi fmt. So here VCT is equal to VC sine 2 pi FCT. Okay, and if you see from this graph, actually see from here where is peak amplitude is actually the highest peak over here, for example VC and minus VC over here. So I just want to show you where is the location of the peak amplitude. Okay, so here if you see from VM here, this one is a VM and this one here is minus VM. Okay, and if you see from the perspective of time, here we have up to, this is what we call as the period of time T. So this is for example this is Tm, so Fm is equal to 1 over Tm. Okay, satu dibahagikan dengan 1 complete cycle for the period. Okay, period of 1 complete cycle. And if you see from carrier, so to complete the time duration to complete 1 complete cycle, okay, so it is Tc. Okay, untuk satu kitaran lengkap masanya adalah Tc, tempoh dia. So Fc is equal to 1 over Tc. And remember that for the carrier signal, for the carrier frequency in AM, so AM has a specific standard for the carrier band. So the carrier band for FC, okay, this is for the AM. this is between 570, for example, until 1700 kilohertz. So this is kilohertz. Yeah. So I delete this one. So this is kilohertz until 1700 kilohertz. So this is roughly uh, the the AM, uh, the carrier frequency for the AM. Okay, so this is the AM band. Okay, this is what we call as the AM band. So AM band. That means the carrier frequency must be chosen between this range of frequency. And later you're gonna see for the FM band, which the radio, um, the FM radio that we always listen in a car, in at home, for example. So that FM band, okay, if FM band, it is between 88 megahertz until 108 megahertz. This one we're gonna learn later about this one. So this is a FM band. Okay, so for FM band, that means the carrier must be between this range of frequencies. So for now, the carrier frequency is between this range of AM bands. So we learn about AM for now. Okay, and the output here is the VAMT. So I will use a black color. Sorry, and yeah. So VAMT, function of time. Okay, VAMT is equal to what you can do is you can derive from the envelope equation peak amplitude of the carrier plus VMT, okay, multiplied with the sine 2 pi f ct. Okay, so this one becomes Vc, if I derive the equations, Vc plus Vm sine 2 pi fmt multiplied with sine 2 pi f ct. Okay, so we play around with the equations. So we get here Vc plus Vm sine 2 pi uh, fmt sine 2 pi f ct. Okay, and this one, so I delete this one. Jam. So this. So this one Vc. Oh, sorry, ada silap sikit. Sorry, I'm sorry about this. So Vc sine 2 pi f ct plus Vm sine 2 pi f ct sine 2 pi fmt. Okay, so when we rewrite the equations, okay, so Vc sine 2 pi fct plus Vm over 2 cos 2 pi fc minus fm t minus Vm over 2 cos 2 pi fc plus fm. So this is for the upper sideband. Okay, so maybe this is too big. So, okay, so here is the on the left, here is the carrier. Okay, here is the lower sideband. Why is this lower sideband? Because this is at the lower frequency. Okay, and here is the upper sideband USB. So from here, then you can draw the frequency spectrum. Okay, so sorry, I will write this one. Saya betulkan sikit sekejap. I rewrite again this one. Vm sine 2 pi fm. Okay, so you see that this VMT, okay, VMT ini, so far up to now, we only use single frequency. Okay, we only use single frequency, satu frequency sahaja, iaitu FM. Okay, frequency of the message. Later, I will show you what if we have more than one frequency input. For example, I have FM1, I have FM2, I have FM3, and so on. Macam mana kalau kita ada banyak? Nanti kita akan lihat. Okay. So for now, we see the single frequency first. Okay. So now once you have the AM equations, then you can draw the amplitude spectrum. Okay, you can draw the amplitude spectrum. So remember, when you draw the amplitude spectrum, remember that you must label the axis. Okay, for example, here is F, frequency versus voltage, for example. Okay, so in the middle we have the carrier component located at FC, and the amplitude is VC. Okay, if you see from here, VC. And then we have the lower sideband, and also we have the upper sideband. Okay, so this one is located, lower sideband is located at FC minus FM. Upper sideband is located at FC plus FM. Okay, and the amplitude for both of these is equal to Vm over 2. This one is Vm over 2. Okay, so regarding the okay, this is for the frequency spectrum. So we see from here we have in terms of voltage, for example. So previously we also learned that the amplitude also can be written in terms of modulation index, for example. So remember that modulation index M is equal to Vm over Vc. The peak amplitude of the input message divide with the peak amplitude of the carrier. Okay, and this one also can be, if you divide this one, you're going to get a value without a unit. It's a unitless parameter. And if you want to get the percentage, we need to multiply with 100%. Okay, we can also rewrite this in terms of percentage. So here you multiply it with 100%. So you get the value in terms of percent. Okay. And remember that when we do the modulation index, we must use a peak amplitude of Vm, peak amplitude of Vc. Which one is that? That one, again, back to the graph over here. So this one is the peak amplitude of the carrier. This one is the peak amplitude of the message. Okay. So, and then, okay. So this one is what we call as the frequency spectrum. Okay, frequency spectrum. Okay. So how we want to draw the waveform, AM waveform. Kita ada lagi satu yang kita panggil sebagai AM waveform. So AM waveform, when we want to draw the AM waveform, okay, so you can practice at home on how to draw the AM waveform. Okay, so this is a V versus time. Previously is V versus frequency, now is a voltage versus time. So normally I do like this. Normally I just drew the dotted line. Okay, and then here is sorry, this is too high, terlalu tinggi sikit. So here is this one. So just draw the dotted line like this so that to guide me to draw the waveform. So I do like this, for example. Okay, so and then here also I do like this. Okay, this is just imaginary line. So when I draw here, I start from here, go down, up, down, up, down. Something like this. Okay, so when you see from here, when we want to label the uh, when we want to give the label, so the highest is what we call as Vmax. Okay, and the lowest here, the lowest peak here is what we call as the Vmin. Similar for the negative side. Here is negative Vmax. Here is a negative Vmin. Okay, so when you draw, you need to put the value. Okay, don't just put like this. You need to put the value. So how much is Vmax? So Vmax is equal to Vc plus Vm. So Vmin is equal to Vc minus Vm. Okay, and you can find the modulation index using these uh, using both of these. So M modulation index. Okay, modulation index. Okay. Modulation index is equal to V mean V mean divide with the uh, sorry. Okay, so uh, so here you can do what you can do. M here is Vmax minus Vmin. Okay, minus Vmin divide with Vmax plus Vmin. Okay, and we can also write a peak to peak value, which is Vmax peak to peak, peak to peak PP minus Vmin peak to peak. Okay, peak to peak means like this, peak to peak. From the highest to the lowest, this is Vmax. Okay, and if you see from here, this one, so this one is Vmin in the middle here. Okay, Vmin. So here, from here until here is Vmin. Remember, this one is Vmin. Okay, so if you rewrite the equations, so this one is Vmax peak to peak plus Vmin peak to peak. Okay, so we get uh, the answer. Okay, so this is what we call as the AM. Ini adalah graph. This is graph is what we call as the AM waveform. So the student always confuse between waveform and spectrum. Waveform is time domain, spectrum is frequency domain. So don't confuse between both of that. Okay. So and then from here, okay, before that, you see from here, from the frequency spectrum here, you see that here the distance here is FM, FM. So from here you can find the bandwidth. So but the bandwidth for AM is equal to FC plus FM. This one upper sideband, the highest frequency minus FC minus FM. So you will get 2 FM. Okay. So in the double sideband full carrier, okay, DSBFC, okay, this is for the double sideband full carrier. Okay, we have double sideband and a carrier. Okay, so it is said that in double sideband full carrier, uh, the message in the message in the upper sideband and also in the lower sideband are similar. Okay, they are the message in the message in the upper sideband and the message content in the lower sideband are identical. So it looks like we send twice to the receiver. Okay, seolah-olah macam kita hantar dua kali sebenarnya. Okay, and if you see that the carrier component doesn't carry any information. Okay, information only uh, uh, carried by the lower sideband and upper sideband component, but the carrier does not carry any information. Kosong, nothing. Okay, so if you see that the carrier has the highest peak, that means it will produce the higher power. So we transmit more than enough power, okay, to the receiver. The information only in the lower sideband and upper sideband. Okay, so that's why you will see later that this double sideband full carrier is quite a waster of power because we transmit more than enough, and also we transmit the carrier which contains a large power but without any information. Okay, that one is in the power topic. So we will learn now about power topic. Okay, so sekarang baru kita boleh masuk ke dalam power. Okay, so semua boleh nampak saya punya screen
Boleh.
Okay. Saya risau kalau semua senyap. Saya risau nanti saya cakap sorang-sorang sampai habis baru perasan semua tak dengar. Okay, sorry. So saya sambung. So power. Power we still use the same equations, the Ohm's equations, which is V RMS square divided with R, or you can use the peak amplitude. Okay, peak amplitude of voltage, which is we can use the equation V square. So this is the V peak actually. So V peak, we normally use this one because we use a peak voltage. So V peak square divide with 2R. So equation power masih sama menggunakan Ohm's law. Dari dulu, kini dan selama-lamanya dia punya equation masih sama. So we have seen about VLSB and VUSB. So ini kita dah lihat sebelum ni. So here if you do like this, so this one is VC, this one is VM over 2, this one is VM over 2. So VM over 2 is also equal to MVC over 2. Okay, remember that M is equal to VM VC. So VM is equal to MVC. Okay, sama aja. So since we have three components, okay, we have three components: lower sideband, carrier, upper sideband. Therefore, the power calculation also must have three components, which is the carrier, lower sideband, and also the upper sideband. Okay, so the way we calculate the carrier power is equal to VC squared divided with the 2R. And then the power for the lower sideband, for example, this is a LSB, for example. So V square over 2R. So that means M square VC square over 4 divide with 2R. So M square VC square divide with 4 times 2R. Okay, this is mathematics. I hope that you can follow this one. So this one is M square VC square divide with 4 times 2R. So if you see from here, it's actually like this, MVC over 2. This one is square divide with 2R. So you see that here is M square VC square divide with 4 divide with 2R. So that's why you get M square VC square divided with 4 times 2R. Okay. So therefore, if we rearrange the equations, you will see that VC square over 2R is actually a carrier power. This one is a carrier power. And if you see here, VC square over 2R, so this is actually power of the carrier. VC square over 2R here is also power component. So that's why the equation is rearranged again to be m square over 4 PC, m square over 4 PC. And finally, we can get the equations total power is PC in bracket 1 plus m square over 2. Okay, ini kalau persamaan ini disusun semula, kita akan dapat PC kurungan 1 tambah m square dibahagikan dengan 2. Remember, this equation is based on this. Okay, it is based on the equation like this. Okay, so that means this equation is only true for double sideband full carrier. Okay, it is not true for other kind of AM. Kenapa macam tu? Why is it like that? So, based on the previous experience, what I saw that students tends to memorize this equation. Whenever we ask about power, students will come out with this equation. Okay, kalau kita tanya je power, student akan keluarkan persamaan ini, which is maybe true, maybe not. Okay, remember when we want to calculate the power, we need to see how many components are there in the frequency spectrum. Okay, so now we have 3 components. Okay, so actually the power, the power P total is actually equal to the PC plus PUSB, plus PLSB. Okay, this is the fundamental equations for the power that you must know. Okay, because we have 3 components. Later you're going to see that other types of AM not have the 3 components like this. Okay, komponen AM jenis AM yang lain ada yang tidak mempunyai 3 komponen seperti ini. Mungkin dia ada satu carrier, satu sideband sahaja. Nanti you akan lihat. But remember, when we calculate the power, we need to sum up all the components power. Kita perlu tambah ke semua power daripada setiap komponen. Dalam kes ini double sideband full carrier, kita ada 3 komponen, lower sideband, carrier dengan upper sideband. So that's why we have 3 component of powers. Okay, so that's what PC plus PUSB plus PLSB. So this one data terbitnya dari okay, you boleh proceed dengan yang ini. VC square over 2R plus M square VC square divide with 4 times 2R. And finally, you get PC in bracket 1 plus M square over 2. Remember this final equation, this one is only true for the double sideband full carrier because we have 3 power components. Okay. So this one is, you see tadi kita dah lihat M square VC square over 8R, 8R. So this one from here, this one is actually PC. Okay, this one is actually PC. So this is a m square v square over 2r. So this is just rewrite again the equations. Okay, so this is not a problem. Okay, so the part below here, okay, the slide wants to show you what happened during the ideal case. Apa yang berlaku ketika ideal case? So the ideal case is when m equals to 1, which is what we call as the ideal modulation. Okay, apa yang berlaku dalam keadaan ideal? So this slide want to show you about during the ideal case. Okay, so the power total can be written as 3 over 2 of PC. Remember previously PT is equal to PC 1 plus m square over 2. Okay, this is for the double sideband full carrier only. So if m equal to 1, that means this one is PC 1 plus 1 over 2. Okay, which is 3 over 2. Okay, so we get 3 over 2 PC. Okay, so power total is 3 over 2 of PC. Therefore, carrier power is 2 over 3 of total. So carrier power contribute of 2 over 3 of the total power. 2/3 daripada total power adalah milik carrier. Okay. Manakala bakinya, okay, the remaining is 1 over 3. So the remaining 1 over 3 of the total power belongs to the sidebands. Okay, sidebands here means upper sideband plus lower sideband. Kedua-duanya sekali. Okay, so the sidebands powers, both of it, contributes 1 over 3 of the total power. So this is during the ideal case, the best case scenario. Okay, therefore, if you see P lower sideband equal to P upper sideband, because it is same height, dia punya amplitude sama, the amplitude is the same, so the power will be the same. Okay, so we divide with 2, kita bahagikan dengan 2. So 1 over 3 divide with 2, so we get 1 over 6. Okay, so 1 over 2, 1 over 3 you divide with 2, so we get 1 over 6. This is for the upper sideband, and also this is for the lower sideband. Okay, 1 over 2, 1 over 6 of the total power. So you see that during the ideal case, dalam keadaan yang terbaik, setiap sideband itu, upper sideband dan lower sideband, masing-masing mempunyai power sebanyak 1/6 daripada total, 1 over 6 from the total power. So imagine if during non-ideal case. Non-ideal case is when m less than 1. Okay, that means P LSB plus P USB are even less than this. Okay, even less than 1 over 3. Okay, PLSB plus PUSB are less than 1 over 3 of the total power. Ini during this is during the non-ideal case. Okay, so in practice, carrier signal will be modulated by several signals simultaneously. So the total modulation index or effective modulation index has to be calculated. So based on this slide, so you see that as I mentioned previously, seperti yang telah saya katakan sebelum ini, information only contains in the upper sideband and lower sideband only, whereas the carrier does not carry any information. So you imagine that the information only, okay, for both of these only contributes 1 over 3. Komponen yang membawa information hanya menyumbang kepada 1/3 power sahaja daripada total. Okay, from the total, so information only contributes to 1 over 3 of the total power. Whereas 2 over 3 is belong to the carrier power, which does not carry any information at all. Okay, dia diperlukan tetapi dia tidak membawa sebarang info. So that's why we can see that from here, we are some sort of wasted of power. Okay, we transmit bigger power, but the bigger portion doesn't contain any information. Okay, so these slides answer to the previous slide. Okay, slide ini menjawab kepada slide yang sebelumnya. Kalau kita lihat, if we see from the slide of advantage of AM, disadvantage of AM, sorry. So these slides, so the power calculations answer these kind of issues, the disadvantage of AM. Okay, so kenapa dia wasted of power? Because majority of the total power belongs to the carrier, where carrier does not carry any information. Okay, so because of this, it is say that this kind of AM double sideband full carrier is not efficient for the transmission because we are wasted of power. We are wasting the power. Okay, itu sebabnya kenapa dia katakan not efficient because of the power. That one is the first thing. The second thing is about the bandwidth. So the bandwidth is also not efficient because we transmit because the information in the upper sideband and lower sideband are the same. So as if we transmit twice. Okay, seolah-olah macam kita hantar dua kali. Okay, so bandwidth is equal to 2 FM. Whereas the information are duplicated in the lower sideband and upper sideband. Information adalah duplicate dalam lower sideband dan upper sideband. So kedua-dua upper sideband, lower sideband membawa info yang sama. Okay, seolah-olah kita hantar dua kali, like as if we transmit twice. As if we transmit twice. Okay, so double sideband full carrier, in terms of bandwidth also, it is not efficient because it requires 2 FM, dua kali ganda daripada message frequency. So the disadvantage of double sideband full carrier can be mentioned as two things. First, in terms of power, it is not efficient because majority of the power belongs to the carrier. Carrier does not carry any information. The second part is that the bandwidth is too big because the information in the lower sideband and the information in the upper sideband is duplicated. So we require more than enough bandwidth. Okay, so in terms of bandwidth also, it is not efficient. Okay, so I continue again. Okay, saya sambung semula. Okay, so maybe we need to calculate, see the example. Okay, so example 3.2, 400 watt of carrier power is modulated to a depth of 75%. Calculate the total power in the modulated wave. So this is for the double sideband full carrier. This is just simply a AM signal, AM signal, which is referring to double sideband full carrier. So you are given PC and you are given M. So you can calculate the total power. Total power using double sideband full carrier equation, power total equal to power carrier in bracket 1 plus M square over 2. So put the carrier power here and then put the modulation index. Remember, you don't need to put percent. Jangan tulis dalam percent. It is 0.75. Don't put 75 here. It is wrong. Okay. Jangan tulis 75. Dia akan jadi salah. You need to put the absolute value, which is 0.75. Okay. So therefore, you get 512.5 watt. This is the total power. Okay, remember this is for the double sideband full carrier, DSB FC. Example 3.3, an AM broadcast station peak carrier voltage of 2 kilovolts. Okay, this is for the carrier voltage. Okay, VC. So VC is 2 kilovolt. Oh, ni dah ada jawapan. and then has amplitude modulated to an index of 75%. So this is M. This is M. With another signal, which is the test tone, has a frequency of 2 kilohertz. So carrier modulate with another signal. So that means this one is the input message. So this one is the FM, frequency of the message. So the station broadcast frequency is 810 kilohertz. So this is using the AM band. So what is this actually? So the broadcast frequency is referring to the carrier frequency. Broadcast frequency is referring to the carrier frequency. So compute the following. Okay, calculate the lower and upper sideband frequencies. So now you have FM, you have the FC. So the FLSB is FC minus FM. FUSB is FC plus FM. So FC plus FM. Okay. So this FC 810 minus 2, so you get 808 kilohertz. 810 plus 2 kilohertz, so you get 812 kilohertz. Okay. The peak modulation voltage. You see that sometimes it use modulation, sometimes it use modulating, sometimes it use input signal voltage. Okay, so it is the same thing. So it is Vm. So Vm you can write based on the M. Okay, so Vm is equal to MVC. So Vm is equal to MVC. So this one is 0.75 multiplied with 2000 kilohertz. Okay, sorry, 2000 volt. 2000 volt. Ah, okay. So ini you boleh kira. So 0.75 kali 2000, you akan dapat 1500 1500 volt. Okay, and then the peak lower and upper side voltage, VLSB, and also the VUSB. So VLSB and VUSB, you can write this is a Vm over 2. Okay, and this is a Vm, so Vm over 2. Okay, Vm per 2 dan juga Vm per 2. So that means you can write here is VLSB equal to VUSB equal to 1500 divide with 2, so you get 750 volt. Okay, and then what? The maximum signal amplitude, Vmax. So Vmax is equal to Vm plus Vc. Okay, so Vmax is equal to Vm plus Vc. So this is 1500 plus 2000 volt. So you get 3500 volt. Okay, for the Vmax. And for the Vmin, if let's say the question asks Vmin, katalah soalan tanya, so it is Vc minus Vm. So this is 2000 minus 1500. So you get 500 volt. Okay, 500 volt. Okay, 500 volt. And this is the answer. Okay, ada jawapannya di sini. Okay. So if you don't understand, you can ask me question. You can always interrupt my lecture. You can ask question, no problem. Okay. If you don't have question, I will proceed to the next topic. Okay. Okay. So this example, So jawapan dah diberikan. Previously, the answer is not given in the slide. So now the answer is there. Okay. So example 3.4, a spectrum analyzer with input impedance. So you are given R, the value of R is 50 ohm, is used to measure the power spectrum of an AM signal. So remember when we just mentioned about AM, this is actually referring to the double sideband full carrier. Okay. At the output preamplifier circuit. So the AM signal has been modulated with a sine wave. So we are using sine function. The effective power PC, okay, the effective power PC is 75745 milliwatt, and each sideband PUSB and PLSB is 125 milliwatt. Compute the following. Okay, compute the following. Okay, so this is referring to the effective power. That means this is uh, when we say about effective power, that means we use a VRMS divide with R. Okay, so therefore, when we want to find the total effective power, okay, total effective power. So you see that total effective power. Okay, before that we need to calculate the the first question asked total effective power. Okay, so since we have all the powers component, PC, we have PUSB, we have PLSB. So power total is equal to PC plus PUSB plus PLSB. Okay, so 745 milliwatt plus 125 milliwatt plus another 125 milliwatts. Okay, so kalau you kira 745, okay, 745 plus 125 plus 125, so you will get 995 milliwatt. So that one is the effective power, because all of the power components given here is the effective power. Okay, so therefore the next question asks about the peak carrier voltage. Okay, so the peak carrier voltage. So the power is, so remember when we want to peak carrier voltage, so that means this one is V peak. Remember the effective power is sorry, the peak amplitude, VC peak, so I write here peak is equal to square root of 2 multiplied with VC in term of RMS. Okay, so you can get the peak amplitude. Okay, so if you see from here, okay, this is for the VRMS, this one. So when we want to calculate the carrier, okay, so this is so first we need to find the, you can first of all you can find how much is a VC peak. Okay, so VC peak, okay, so VC, sorry, you can first, you need to find the VC RMS because you are given the effective power. Okay, VC RMS is equal to power, okay, square root of power PC multiplied with R. So PC multiplied with R. So here you get how much is this? So PC adalah 745. So 745. So this is square root of 745 times 50. So this is 37 point. This is 37.250. 250. And then you square root this one, you get 6.103. So this is 6.103. Okay, So this is RMS. So when you 1032 saya buat betul. Okay. So VC peak, so VC peak amplitude is equal to square root of 2 multiplied with 6.1032. Yes, square root of 2 multiplied with 6.1032. So we get 8.63. 8.6312. So this is equal to 8.6312 volt. Okay. So this is a peak amplitude. So sama lah dengan ni. 6312 or 6313. So the next question asks, how much is the modulation index? So modulation index, remember that we need to use the peak amplitude. Okay. So modulation index. So okay, here so in terms of power, you can use these equations. Okay, doesn't matter if you use the RMS value, because if you use RMS, that means both side must use the RMS. If you use the peak amplitude, that means both side must use the peak amplitude. So it will produce the same answer. Okay, dia akan menghasilkan jawapan yang sama. Dia cuma nisbah dari segi square root of 2 sahaja. Okay, so based on the
Doktor,
yeah.
yang VC dukungan RMS ni kan yang PC darah R kan.
Okay.
Kalau kita ikut yang formula yang dekat sini sama je ke? Sebab yang ni lepas pada tu baru doktor darab dengan 2 and which is square root.
So soalan maksudnya yang ini soalan yang ni ke? VC peak ni.
Ya. I mean doktor bila saya jangan doktor macam buat satu-satu lah, which is dekat sini dia letak 2 PCR kan. Dekat sini doktor terus square rootkan dia PC darah R. So which is yang dalam ni doktor kira cuma square root ni biar je dululah kan. Lepas tu baru dapat yang 6.1032 and after that baru doktor darab square root 2 kali dengan ni. Which is kalau boleh ini yang jangan kira panjang dia ke or
Yeah.
I mean the
So
step.
I just want to show the detailed calculation macam mana sebenarnya. Sebab remember that the basic part is that V peak. Okay, V peak. Sorry. So V peak is V peak is equal to VRMS. Saya punya So V peak is equal to VRMS multiplied with square root of 2. Okay. Ataupun you can write VRMS is equal to V peak divided with square root of 2. So this is the fundamental equations. So this slide shows the complete equation. So I just rewrite again. Saya cuma rewrite sahaja supaya pelajar lebih jelas macam mana nak mencari peak amplitude tersebut. So kalau you dah mahir, you can straight away using this kind of equations, the complete equations like this. Okay, so you akan dapat jawapan yang sama. Sebab the power that given this power, all of this power is in term of RMS. That means the voltage is in term of RMS. So we need to find the peak amplitude. So if you ask me, is it the same? It is the same. Dia sama saja. Kalau guna cara yang ini ataupun yang saya kira ni lebih saya buat one by one supaya kamu nampak.
Okay doktor.
So okay, in order to find the modulation index from the total power, so you can write here power total equal to PC plus 1 plus m square over 2. Okay, when we do the modulation index, remember both of it, you can use either both of it as a RMS or both of it in term of peak. Okay, apabila kita mengira modulation index, okay, VC, sorry, VM over VC, okay, VM over VC. So either we want to use both as RMS or both as peak amplitude. Dia mesti sama. Otherwise, you akan dapat jawapan yang berbeza. Kenapa saya katakan begitu? Because if you use, even though if you use a RMS value, okay, even though kita menggunakan RMS value, dia punya nisbah masih sama. Okay, so that's why here this slide use the total power equations. Okay, so when you take out the m here, okay, even though you use a RMS power, okay, so we still can get the modulation index, because the modulation index is the ratio nisbah, sama ada kedua-duanya sebagai RMS, VM sebagai RMS, VC RMS, ataupun VM dan VC sebagai peak amplitude, okay, or VM and VC as a peak amplitude. Okay, so if you see from here, if we rearrange the equations, m equal to square root of 2 times PT over PC minus 1, and then you put inside the equations, you will get 0.8192. Okay, so this is from the total equations. You can also find the value of VM. Okay, you can also find the value of VM from 1 to 5 millivolt. Okay, so this is if you do the if you do from 1 to 5, this is a VM RMS, sorry, VM RMS over 2, okay, divide with R. Okay, so that means VM RMS must be multiplied with the square root of 2, so you can always get the VM, and then from there you can find VM over VC. Okay, sama juga kalau kita kita cari VM daripada PUSB ataupun PLSB, kita boleh dapat nilai VM peak, and then we can divide with the peak VC. Okay, itu cara panjang sikit lah. Okay, so once we get the modulation index, okay, we can find the modulation index in term of percent by multiplying with 100%. Okay, so we get 81.92. So after we get this one, 81.92, we can get the VM peak amplitude. VM peak is equal to modulation index multiplied with VC peak. Okay, VC peak yang kita telah dapat tadi, that we already counted before. So 0.8192 multiplied with peak of carrier 8.6313, so you get 0.078. So this is the peak amplitude of the input message. Okay, so from there you can find the if you want to find the RMS. So this question asks RMS or not. This question doesn't mention about RMS. Actually, you can stop there about the peak voltage. Dia tidak katakan secara spesifik adakah peak ataupun RMS value ini. So VM peak is 7.0708, or if you want to find the VM RMS, you need to divide peak value with square root of 2. So the RMS value for VM is 5 volt. Okay. So the next question asks, how much is the VLSB and also VUSB? How much? Berapakah nilai VLSB dan juga VUSB? Okay. So here, if you see from here, the lower and upper sideband voltage. So this is asking about the peak amplitude of the lower sideband and also the upper sideband. So normally when we want to find the LSB and USB, normally we find in terms of peak amplitude. Okay. So VLSB is equal to VUSB, which is M multiplied with VC. So if you want to find the peak value, that means VC must be the peak value. Okay. So this one is MVC. So ini dalam RMS ke apa ni? So MVC. So if you write 0.8192, okay, multiplied with M in terms of peak value, the peak value we get here is 8.6313 untuk carrier, 8.6313. Okay, so you get 7 point, okay, and then divide with 2, so you get 3.53. Okay, 3.53 is the peak amplitude for the this one, peak amplitude for the VLSB and VUSB. So this answer provides you with two values. First, the peak amplitude of the VLSB and also VUSB, and also it gives you the value of the RMS. Okay, so if you want to find the RMS, that means you must multiply MVC RMS, MVC RMS divide with 2. Okay, so if you 0.81192 multiplied with VC RMS, you get previously is 6.1032. This one that I get previously, 6.1032. So times 6.1032, okay, 6.1032, and then divide with 2, so you get the answer for the RMS value. 0.8192 multiplied with 6 point, this one is 6.1032 divide with 2, so you get 2.4998 or 2.5. Okay, for the RMS value of the VUSB VLSB. So soalan ini dia agak mengconfusekan kita dengan RMS value, so don't be confused. RMS or peak amplitude, you must be consistent. Either you want to use a peak amplitude or you want to use the RMS value. Okay. Normally, in the test, in the final exam, we normally ask you about peak amplitude. Easy for you to calculate. Lebih mudah untuk you calculate. Okay. So this is the RMS value. Okay, 2.5, and this is the peak value. Okay, peak value. Selesai. And then the last question. So the last question asks about what? Yeah. So the last question asks, sketch the waveform that you will see with an oscilloscope if it is placed in parallel with the spectrum analyzer. So the question asks, sketch the EM waveform. That means you need to do the time domain graph. You need to do the time domain graph. Okay, like this one. Okay, so again, as I said previously, you need to practice on how to do this. Okay, you need to practice on how to calculate, on how to simply draw the waveform like this. So you see that I just redraw again like this. Okay, cuba practice. This must be V or versus time, and the peak here is Vmax, and here is over here is minus Vmax. Sorry, saya punya stylus ni kena tukar lah. And then we have the Vmin over here, Vmin, and here is the minus Vmin, minus Vmin. Remember when we do the time domain, we must use a peak value. Okay, apabila kita membuat dalam time domain, kita merujuk kepada peak value. We are not using the RMS value because the RMS is slightly lower than the peak value. Okay, so when we draw the time domain, we are actually using the peak value. Okay, so Vmax, you can find the Vmax is equal to VC peak, okay, plus okay, plus VLSB peak plus VUSB peak. Kenapa dia kata dua ni? Actually, it is like that because this is a VM over 2. So that's why you get a VLSB and also VUSB. So it is actually a VC plus VM. Okay, sama je. Because VLSB is VM over 2. VM dibahagi 2. So dia adalah hasil tambah VLSB dan juga VUSB. This is for the Vmax. Okay, this is Vmax. This is Vmax. Okay, and VC minus Vmin peak value, and you get the Vmin. Kita akan dapat, so Vmax is equal to and then hilang pula is sekejap, sorry about that. So Vmax equal to VC. Okay, tak apalah, saya cakap je lah. So Vmax is actually equal to VC plus VM peak value. Okay, so previously we get a VM peak equal to 7.0708. Okay, so if you plus with the VC peak, you get 15.7023. Okay, and for the Vmin, we get a VC minus VM or VC minus VLSB minus VUSB, so we get 1.5603 volt. Okay, so when you draw the waveform, you need to label both of these value. Okay, you perlu labelkan kedua-dua value ini. Okay, so 15 is here, 15.70 is here, 7023 is here. Don't just write Vmax, you need to put the value. Okay, in the exam, in the test, when it is asked to draw the waveform, you need to label the value, not just to label the variable. Bukan label sebagai variable, you need to put the value. Okay, so V mean here is 1.5603. Okay, 1.5603. Sorry, saya punya ni ada masalah. So ni so as in the picture, seperti dalam picture ini yang mana ada Vmax, ada Vmin. So when the question asks you to draw and label, First, you need to label the axis, voltage versus time. Second, you need to label the Vmax. Third, you need to label the value of Vmin. That's it. You get the full marks for that. Okay. Ada soalan nak tanya berkenaan dengan example ini? Do you have any question you want to ask? Previously, when students draw the waveform, they just draw this AM waveform without anything, without axis, without label. So you maybe not have, maybe you get 1 marks or maybe no marks at all. Okay, so you need to draw properly and label it. Okay, no need to draw it very beautiful, just sketch it. As long as we can see the difference, that's enough. Okay. So if you don't have questions, I will proceed with the next topic. Okay. This is important about modulation by several sine wave. Okay, to calculate the resulting power, let V1, V2, V3. So all of these is all of these are the message, the peak amplitude of the input message. Okay, that means we have a VM1, VM2. Okay, VM1, we have VM2, we have VM3. Okay, and so on, dan seterusnya. Okay, and the way we calculate the total modulation index, we need to divide each of these input message peak amplitude with over the carrier voltage. So VM1 over VC, VM2 over VC, VM3 over VC. Okay, kita perlu buat quadratic summation. Okay, like this. Okay, so this is, if you see here, this is M1, this is M2, this is M3, and so on until M of N. Okay, so M square plus M square plus M square plus M square. Okay, so the total M is M total square divided with, so PC plus 1 plus M total square divide with 2. Okay, so how do we get later I will explain about that. So first of all, this is the total power. Okay, this is the total power for the uh, double sideband full carrier. Okay, double sideband full carrier, but now we have more than 2 sideband. Maybe we have more than 2 or 2, 4, 6, 8. Okay, so each input will produce 2 sideband. Okay, each input will produce 2 sideband. So kalau you ada satu input, you akan produce 2 sideband, lower and upper. If you have 2 input message, for example, you have VM1, VM1 and VM2, so you will produce 4 sideband. If you have 3 input message frequency, you're gonna produce 6 sidebands. Ini saya akan tunjuk nanti sekejap. So based on the power, you can see here, we can also use the current, okay, current equations. So I total square times R. So this is the Ohm's law. We still use the Ohm's law. Okay, I square R. This is for the carrier power. Okay, this is for the carrier power multiplied with the M square over 2. So this is for the single input message. Okay, so this is for the single input message. Okay, so you cancel out the R, so you get IT over IC. Or if you have more than one input message, you need to change to MT square. Okay, so I want to show you about this one. So if you remember that, okay, let's say we have a VCT over here. Okay, VCT is equal to VC sine 2 pi FCT. So, and then let's say we have a VMT is equal to, for example, here is, for example, I have two input message, for example. So here is VM, so VM1 sine 2 pi FM1T, the first frequency, plus VM2 sine 2 pi FM2T. Okay, if I have more than 2, I need to plus more than that. Okay, so now I just want to show you about multiple input frequencies. Okay, so when we derive the AM equations, VAMT, we derive based on the envelope equations. Remember, envelope equation is VC plus VMT multiplied with sine 2 pi FCT. Okay, so from here, you see that I can make a big bracket here. So VC plus VMT now we have two input frequencies, for example. Okay, so this is VM1 sine 2 pi FM1T plus VM2 sine 2 pi FM2T, close bracket, multiplied with sine 2 pi FCT. Okay, so listen carefully. So I hope that you understand about this. So if I uh, derive the equations again, so this one becomes VC sine 2 pi FCT plus VM sine, so this one becomes 2 pi FCT sine 2 pi FM1T. So saya darabkan satu persatu. Saya darab, I multiplied one by one. So I multiplied with this, I multiplied with this, and I also multiplied with this. Okay. So plus VM, sorry, this is VM1, this is VM2, sine 2 pi FCT sine, this one is, sorry, sine 2 pi sine 2 pi FM2T. And if we kalau kita kembangkan equation ni, if we derive the equation, if we write the complete equation, it will become something like this. FC sine FC sine 2 pi FCT plus VM1 plus VM1 over 2 Okay, so this one becomes cos. So according to trigonometry identity, sine and sine becomes cos and cos. Okay, dia jadi cos. So cos, sorry about that. So cos cos 2 pi fc fc minus fm minus cos 2 pi. This is fm1. Okay, 2 pi fc plus fm1. This is ada t di sini, f1t. Okay, so sorry about this. So I erase this one. Yeah, sorry, tak cantik. Saya padam balik. So this is cos. I rewrite again. Sorry about that. 2 pi in bracket fc minus fm1 t minus cos 2 pi for the upper sideband fc plus fm1 t close bracket, and then plus plus the second component, the second frequency of the input message. Okay, so this one becomes vm2 over vm. Okay, so this is vm2. Okay, and then big bracket, repeat again the process. So cos 2 pi fc minus fm2 t, okay, minus cos 2 pi fc plus fm2 t close bracket. So you see that here I have how many components I have? I have one carrier, the first lower sideband, the first upper sideband, the second lower sideband, the second upper sideband. Nampak saya ada, now I have 5 components. Okay. So I just want to show you about this multiple input frequency so that you can have more understanding about this. So when we draw the frequency spectrum, okay, apabila kita melukis frequency spectrum, okay, it becomes like this. So this is for example voltage versus frequency, for example. So in the middle we have the sorry, saya punya ni tak cantik. Sorry about my drawing is not very good. So this is located at fc, and then we have the first input message. Okay, we have here is okay over here. So this is located at fc minus fm1. This is located fc plus fm1, and the amplitude is, this is a vm1 over 2, this is vm1 over 2. Okay, and then for the second input message, so this is located at fc plus fm2, and then here is fc minus fm2, and the amplitude is vm2 over 2, vm2 over 2. Okay, so you see this one. So how do we calculate the total power? Okay, so first of all, when we want to write the when we want to write the modulation index, so modulation index M total is equal to, as stated in the slides, in the lecture slides. So this one is Vm1 over Vc square plus Vm2 over Vc, sorry, so Vm2 over Vc square. Okay, so you will get the answer. Okay, or you want to multiply it with 100%, you can write x multiplied with maybe for example a multiplied with 100%. So you get the answer in terms of percent. Okay, either you want to write without percentage, or you want to write in terms of percentage. Okay, so this is about total modulation index, because we have two input message and one carrier. Okay, and then what about the total power? So when we want to write the total power, of course we have 5 component of powers. Okay, in this case we have 5 component of powers. So that means P total is equal to PC plus P LSB 1 plus P LSB. Sorry, I can put here is PUSB. PUSB 1. It's up to you. I just want to show you the first input, and then plus the second input. PLSB 2 plus PUSB 2. Okay. So this one is VC square over 2R using the peak amplitude. So plus this one, you see that this is VM1 over 2. So this is Vm1 over 2 square divide with 2R. Okay, so that means you get Vm1 square over 8R. Okay, and then plus Vm1 over 2 square divide with 2R plus Vm2 over 2 square divide with 2R. So this is the second frequency, the second input frequency, plus Vm2 divide with 2 square divide with 2R. So what you get is actually here VC so this is okay, VC square over 2R. Just rewrite again. Saya cuma rewrite again. So this is a VM1 square divide with 8R plus VM1 square divide with 8R plus VM2 over square 8R plus VM2 square divide with 8R, like this. So you see that when I write the power equation, okay, when I write the power equations, I am using the equations based on the equations that I have written here. So I see from the equation I have 5 components, and then I draw the power spectrum. I have 5 components in this example. So kalau you ada 3, if you have the 3 input, that means you have 6 sidebands plus carrier. If you have 4 inputs, you're gonna have 8 sidebands plus carrier. Dia sepasang, dia akan keluar. Satu input akan keluar sepasang output. Okay, setiap input akan mengeluarkan sepasang output. Okay, so based on these long equations, actually this one, okay, actually this is equal to PC 1 plus MT square over 2. You will get the same answer. Okay, you will get the same answer. Even though you have many, okay, but in a simple way you can calculate like this. Okay, you akan dapat jawapan yang sama. Okay. So back to this slide. So ni kalau ada soalan nak tanya, tak? Do you have question to ask about this multiple inputs things? So I suggest you try to understand this one because this is important for you. So you need to understand about this. Okay. For your information, these multiple input topics only come out in the previous semester only once. Hanya sekali pernah keluar. Itu pun pada semester kedua 2014-2015. And after that, we haven't come out with the multiple input. Okay. So I suggest you to understand about this so that you can answer for the test and final exam. Okay. So if you don't have any questions, I will proceed with the slide. So for students, if you feel tired, you can have a break. Okay, you can have a break, but I will continue. Okay, my lecture. Pelajar-pelajar masih ada di sana? Okay.
Ya,
Okay.
Ya, Doktor, I'm still here.
Okay, thank you.
Ada doktor.
Saya bila senyap saya risau. Am I disconnected or am I still online? Okay, so if you respond like that, so I know that I'm still online. Okay, so ini boleh macam tadi boleh tadi. So kalau you dah if you okay, so here I have show you that for the multiple input for the this is for the case of double sideband full carrier. That means every input message will produce a pair of sideband. Setiap input message akan menghasilkan sepasang sideband. It doesn't matter if you have more than 2, 3, 4, 5 inputs. So the output, you need to multiply with 2, so you have a pair of sideband for each input message. Okay, and what I want to show you also is that when you want to calculate the power, first you need to know the equations. From the equations, you can draw the spectrum. You can see how the spectrum looks like, and then from there you can calculate the total power. Okay, so this is the fundamental equations for the power. Ini yang asas. Okay, selepas itu dia bergantung kepada jumlah komponen pada equation and also pada spectrum, power spectrum. And then from there, you can calculate the total power. And only for the double sideband full carrier, you can use this equation. Hanya untuk double sideband full carrier sahaja, you boleh menggunakan equation ini. Untuk double sideband full carrier yang lain, you tak boleh menggunakan equation ini. Okay, you tak boleh gunakan equations, sorry. Okay, for other than double sideband full carrier, it is safer to use these fundamental equations. Okay, these fundamental equations can be used in all type of power calculation. Ni secara basicnya dia adalah seperti itu. So what I'm worried is that students tend to use the simple equations, the final equations, without knowing that this is only true for the double sideband full carrier only. Okay, remember this only true for the double sideband full carrier only. Okay, nak lebih selamat, better you gunakan equation yang ini. Okay, this equation is more better. Okay, because you are based on the component. Berapa banyak komponen pada equation, pada power spectrum, itulah dia jumlah powernya. When we want to write the total power, we need to sum. Okay, sum all the power components. Kita tambah semua power components, kita dapat dia punya total. Okay. So I proceed with the next slide. So if you don't have questions, I proceed with this example 3.5. Okay, students, if you have question, you can always interrupt me. You can always ask me question. So example 3.5, the antenna of an AM transmitter is 8 ohm. When only the carrier is sent. Okay, so if you draw the picture something like this is the transmitter. Okay, this is the input, and this is the antenna, for example. Okay, this is the antenna. We have the carrier over here, so this is this is the BMT. This is a VCT. Okay, so it is said that when there is no carrier, okay, apabila tidak ada when there is no input, okay, when there is no input, that means the system only receive carrier. Okay, so the output is 8 ohm. Okay, so that means this is direct to the output, which is this one is referring to the I carrier. Without the input message, the output only produce the carrier. Okay, so when there is a input message, apabila ada input message, the current becomes 8.93. 8.93. So the current becomes 8.93 when there is an input message. So what is it actually? So 8.93 is actually referring to the total current, I total. So I total is the mixing of input message and also the carrier components power current. So that's why you get the I total. I total mengandungi dua komponen, iaitu message dan juga carrier. Okay. So from here, from this equation, from this question, you can predict the answer. Okay. So find the percentage of modulation and the antenna current when the percentage of modulation changes to 0.8. So there are two questions here. Okay, ada dua soalan di sini sebenarnya. So first, find the percent modulation. Okay, so this one you can use IC or IC and also IT based on the previous this one. Okay, you can use IT over IC. Okay, so modulation index is equal to IT divided with IC. Okay, so yeah, IM or IC. So so I'm not recommending using these equations. So it is actually M equal to IT over IC. I total divide with the I carrier. Okay, which is this one is equal to square root of 1 plus M square over 2. Okay, so we need to use I total divide with I carrier. So 8.93 divide with 8, so you get 1.1163, or in terms of percentage, it is equal to 111.63. Okay, 111.63%. So this is considered as over modulation. Okay, over modulation. So after that, the second question. Okay, so soalan ini, kalau you lihat, what you need to do is IT over IC. Okay, so 8.93 divided with 8 ampere. So you get 1.1163, which is equivalent to 111.63%. Okay, this is considered as overmodulation. So this is the first equations. The second question asks, what happened if find the antenna current, okay, antenna current when the percentage of modulation change to 0.8. What is antenna current? The current to the antenna, okay, current yang melalui antenna. What is it actually? So the current that go through the antenna is actually the total current. Dia adalah total current. So you need to find the new I total. Kamu perlu mencari I total yang baru sekiranya if given the modulation index 0.8. So now the modulation index is 0.8, you need to find the total current. What about IC? IC is still the same. Okay, I total masih sama, iaitu I carrier masih sama. IC is still the same because we assume when there is no input, we still using the same carrier. Okay, carrier is still the same, but maybe in this case, the input signal is changing. Okay, input signal mungkin berubah pada ketika ini. Input signal mungkin menggunakan input signal yang lain, for example. So IC, we still use IC is equal to 8 ampere. Okay, so we need to find the current to the antenna, which is the I total. Okay, so I total is equal to M multiplied with IC. Okay, so I total is equal to M multiplied with IC. Okay, so you get 0.8. Okay, because you are given 0.8. So 0.8 multiplied with 8, so you get 6.4 ampere. So 6.4 ampere. Finish. That's it. Okay, so this is quite easy, straightforward. Okay. Okay, do you have any question you want to ask about this? Ada soalan nak tanya? Okay, if you don't have question, I will proceed with the next topic. Okay, so again, I want you to interrupt me if you have questions. If you don't have question, I will proceed until the end, sehingga masa yang terakhir. Okay, the next topic is about types of AM, the family of AM. So previously we have seen double sideband full carrier. So actually AM has another siblings or family member. Okay, the other one is the oldest is the double sideband full carrier. Yang paling tua adalah double sideband full carrier. That one is the oldest technology. And then come out with the reduced carrier. And then single sideband, and then vestigial sideband. Okay, so for AM, remember for AM double sideband full carrier, we have one carrier and then one pair of sideband. Okay, where for the AM double sideband full carrier, the carrier amplitude is much higher than the lower sideband and upper sideband. For the double sideband reduced carrier, what happened is that the carrier amplitude, the carrier component is smaller, reduced in terms of amplitude. Okay, the word reduce here, reduce in terms of amplitude. So that means the sideband amplitude or the sideband power is larger than the carrier component. Okay, and then for the single sideband, we have two options. Either we want to use with carrier. Okay, so with carrier, that means we have carrier, we have upper sideband, or we have the lower sideband, either one. Okay, we can have either one, lower sideband with carrier or upper sideband with carrier. So this is with carrier, WC. Okay, sorry. This is without. It's without carrier. So this is with carrier. Sorry about that. This is I erase this one. So this is single sideband with carrier. Okay, this is with carrier. So that means carrier plus lower sideband or upper sideband, salah satu. And we also have without carrier. Okay, without carrier. That means no carrier component. And we have either upper sideband or lower sideband. Hanya ada satu saja. Okay. What about vestigial sideband? So vestigial sideband, you're going to see later that we have the carrier, we have the upper sideband. Okay, we have the upper sideband, and we have a smaller lower sideband. Okay, smaller lower sideband. So the amplitude of the sidebands are not equal. Okay, in terms of amplitude, it's different. In terms of bandwidth, is also different size. Okay, the distance from carrier to the upper and also the distance from the carrier to the lower sideband is different. This one, vestigial sideband, is used in the TV broadcasting, television broadcasting, where it carries both video and also the audio signal. Okay, we will see later about that. Okay, power content of the double sideband suppressed carrier. This is another one what we call as the suppressed carrier. Suppressed carrier is also under the category of reduced carrier. So suppress means that we suppress the carrier component. We reduce to the minimum or we remove completely the carrier component. Okay. So dalam kes ini, biasanya suppressed carrier, normally in the suppressed carrier, that means we suppress the carrier completely. Okay. And then we have the this one. Okay, we still have the uh, USB and also the upper side, lower sideband. Okay. Later, you're gonna see that if we theoretically, if we suppress the carrier component, we can increase the amplitude of the sidebands. Theoretically, okay, secara theoretical calculation nanti kita akan lihat. Okay, these equations may be confusing to you. Maybe I will explain to you. You see that here, the power of double sideband suppressed carrier. Okay, power of double sideband suppressed carrier only involve lower sideband and also upper sideband. They have two components without the carrier. Okay, so secara full mathematics equations, you see that the total power is from limit minus t over 2 until t over 2. So from the lower to the upper. Okay, v square over r. Where is r? Remember, we always use the equation of power, v square over r. Okay, kalau dalam RMS. So in this case, how come there's no r over here? Kenapa tidak ada r? Okay, so class, remember, we still use the Ohm's equations for power. Masih sama. So dalam case ini, in this case, actually, the r is assumed as 1. Okay, normally if you read many literature books, they only write like this because they assume that the resistance is unity, is equal to 1. So actually there's a r over here. Sebenarnya ada r di sini actually. Okay, but the r is assumed as 1. So that's why it doesn't, this equation doesn't mention about R. Okay, so the equation of double sideband full carrier, V square Vm square cos 2 pi FCT. So you see that this one is Vc square Vm square. So you see that here, if you see Vm square, this is supposed to be cos square. Okay, this sepatutnya menjadi cos kuasa 2 because we do the quadratic over here. So that's why cos and cos square, according to trigonometry identity, it becomes 1 over 2, 1 plus cos 2a, 2a. A is the FC in this case. Okay, so this is cos square, so that means 2 times the frequency of this, so you get 4 pi FC. So if we put Vm square outside, so this is so it becomes like this. So this is so you see that the component here, okay, the component cos 4 pi FC. If you do the integral, it will contribute a smaller value. It will contribute a small value. Therefore, it can be omitted in compared to the Vm square. So nilai frekuensi tinggi ini, this one it's a very small amplitude. Okay, if you do the multiplications, so that's why in the final equations, this component can be omitted like that. So it becomes a Vm square. So Vm square, this is when you do the square, that means you will produce the power of the message. Okay, so that's why Vc square over 2 times power of the message. So this is quite confusing. I'm not expecting you to memorize this equation. Jangan hafal. Don't memorize these equations. So this is simple actually. So what you need to do is that the total power for the double sideband suppressed carrier, it is like this. It is a PLSB plus PUSB. PLSB, okay, LSB plus PUSB. Okay. ELSB plus PUSB. That one is the total power for the double sideband suppressed carrier, which is from here. Okay, because double sideband suppressed carrier, it only contains sideband component without the carrier. Okay, because the carrier has been suppressed. Okay, so actually this is like this. Okay, dia seperti ini. Later we're gonna see about this, so don't worry about that. Okay. Okay, this is for the double sideband suppressed carrier. You see, this is using the MATLAB. So you see, for your project, is actually we want to produce this kind of graph. Untuk project kamu, sebenarnya kita nak melihat this kind of graphs, but you are making the GUI so that easy for other people to learn about AM, for example. You put inside the values and it will produce the graphs like this. For example, contoh seperti ini. So when you do your project is actually to help other people to get more understanding about the topic. For example, here is the AM. So if you have a proper learning GUI like that, so you can normal people can just put inside the values, and it will produce the output, how the output looks like. Okay. So the first one here is the carrier signal. So you see the carrier signal is very close. The ripple is very close to one to one. The ripple is very close to one to another. That means it is a higher frequency compared to the message. Okay, the input message is this one. So this is the uh, double sideband suppressed carrier waveform, and this is the power. This is the spectrum, frequency spectrum. So you see that there's no carrier component. The carrier component has been suppressed. Okay, and we only have the LSB and also the USB. Okay, we only have these two. Okay, so how to draw this waveform? So I want to show you how to draw the waveform. So when you draw the waveform, the things that need to be considered is over here. Okay, this is very important thing to show. Okay, ini adalah perkara penting yang perlu ditunjukkan apabila kita melukis double sideband suppressed carrier waveform. What is this actually? This is what we call as the um, phase deviation. Okay, perubahan fasa sebanyak 180 degree. Okay, this is what we call as the 180 degree phase deviation. Okay, so maybe I need to show you this one. Okay. So when we draw the waveform, okay, this is a v versus time. So this is actually the v component. So I just want to show you that like this. So when we draw, when you draw, you can do like this. Okay. Okay. So see from here, you see that from here, I'm supposed to go down. Okay, if I continue, okay class, if I continue the graph, it will looks like this. Dia akan oh, it happens again, sorry. Okay. Okay, class, you see that if I continue drawing, so my waveform gonna looks like this. However, in the double sideband suppressed carrier, it is not like that. Dia bukan seperti itu. So what happened is that at this time, okay, pada ketika ini, if I draw a small, okay, kalau saya lukis di atas ini, sorry, saya buat di atas ini. Okay, this the green color here is the green color here is the VMT. Okay, I just want to show you that here. So in the double sideband suppressed carrier, the important thing happens when the input message goes from positive to negative or from negative to positive. Okay, perubahan yang ketara, the most critical changes happen when there is a zero crossing, okay, from positive to negative or from the negative to positive. Okay, what I mean is that when the input message change polarity from positive to negative, the output will have uh, the output phase will change 180 degree. Perubahan pada output, fasa output berubah sebanyak 180 darjah. So at the output side, instead of going down, if you see from here, instead of going down, the wave will go up like this. Okay. So this is what we call as the 180 degree phase shift. Sorry, tadi saya sebut deviation, silap. Sepatutnya dia adalah phase shift. Perubahan fasa sebanyak 180 darjah. Okay. So this point highlights the 180 degree of phase shift. Perubahan fasa pada output sebanyak 180 darjah berlaku pada ketika input message berubah polarity, sama ada daripada positif to negatif atau daripada negatif to positif. Okay, so again here, if you see from this, when it is changes here, this is also happen. Okay, if I continue the drawing, kalau saya teruskan drawing, okay. So you see that here, instead of going up, it will go down like this. Again, there's a 180 degree phase shift. Okay, berlakunya 180 darjah phase shift, perubahan 180 darjah. Okay, so this is, when you draw, you need to highlight this 180 degree phase shift. Okay, kalau you tidak melukis ini, maknanya you punya drawing salah. Based on the previous exam, previous semesters, students did not shows the 180 degree phase shift. So therefore, the answer is wrong. Okay, you cannot simply draw like that. Don't draw simple like that. You need to highlight the important things. Okay, so this is what we call as the waveform. So when you draw the spectrum, okay, spectrum, we only have this one. Okay, so there's no carrier component, though this is FC. This is FC plus FM. This is FC plus, sorry, this is FC minus FM. Okay, so this is a voltage versus frequency. What about the amplitude? Okay, what about the amplitude? Amplitude here is not equal to Vm over 2. I just put V1 here and also V2. Remember, V1 equal to V2, but it is not equal. Okay, not equal with Vm over, dia tidak sama dengan Vm over 2. You will see later that, okay, you will see later that V1 equal to V2 and it is larger than Vm over 2. Dia lebih besar daripada Vm per 2. Macam mana boleh dapat macam tu? It is based on the equations. Nanti kita akan lihat macam mana bentuk equationsnya. Okay, so so maybe I can show you here. Okay. So saya terus buat equation supaya kamu boleh nampak. So V DSB FC. So DSB SC, suppressed carrier, function of time. So sorry. When we calculate the power, nanti saya akan tunjuk lah biar nanti power multiplied with this one. So okay. So this is actually based on the multiplication Vc of t multiplied with Vm of t. Okay, dia sebenarnya daripada equation ini. So this is actually Vc sine 2 pi fct multiplied with Vm sine 2 pi fmt. Okay, sine 2 pi fmt. So what you get from here is actually Vc Vm sine 2 pi fct sine 2 pi fmt. Okay, so what happened is that the output gonna be like this: Vc Vm over 2 in bracket. Based on the trigonometry identity, sine and sine become cosine. So this is cos 2 pi fc minus fm minus cos 2 pi fc plus fm. This one and here the t, and this one and then close bracket. So when you draw from here, okay, you see that the sideband amplitude is Vc Vm over 2. Okay, so when I draw the frequency spectrum, okay, aku pilih saya melukis ini. What happened is that the amplitude is actually Vc Vm over 2, which is larger than Vm over 2. Dia lebih besar daripada Vm over 2. Okay. Nah, nanti kita akan lihat lebih lanjut lah. So the modulation process is we normally use the what we call as a balance modulator. Okay, the symbol of X. Okay, we call it as a balance modulator. Okay, balance modulator. Okay, so we have the input here. So this is a VMT. This is the VCT. Okay, so you see that here is X sign. Okay, this is a, if you see, this is the X symbol. So that's why you need to do the multiplication process. Okay, so that's why you get the at the output you're gonna get the VDSB as C function of time. So that's the story of double sideband suppressed carrier. Okay, double sideband suppressed carrier. Equationnya seperti itu. And then I continue again my slide. Okay, I continue again. Advantage of double sideband suppressed carrier compared to the double sideband full carrier. AM here is double sideband full carrier. In terms of power conservation, easy to generate. Okay, why power conservation? We managed to save some power because you see that we don't have the carrier component. Okay, we managed to suppress the carrier component, so that's why we managed to conserve the power. Okay, dari segi power kita lebih menjimatkan power kerana carrier tidak membawa sebarang info. The carrier doesn't contain any information, so if we suppress the carrier, because most of the power contains in the carrier component, so if we suppress the carrier, that means we can conserve the total output power. And then in terms of disadvantage, again, rarely used because the signal is difficult to recover at the receiver, requires carrier insertion complex circuit. And another thing is that the bandwidth is still the same as double sideband full carrier. If you see from here, the bandwidth is still the same as 2 FM. Okay, bandwidthnya masih sama 2 FM. So dari segi bandwidth, dia masih besar. Okay, and then what? The single sideband. Single sideband, we have two types. Single sideband with carrier. So you see that here, this is the carrier, this is the input message, and this is the single sideband with carrier waveform, and this is the single side bandwidth carrier frequency spectrum. So you see that we have the carrier component, we have the upper sideband, but we don't have the lower sideband. Okay, the lower sideband is not here. So we use a filter to filter out the lower sideband in this case. Okay, so you can also choose a lower sideband and you can remove the upper sideband. So you can choose either one, upper or lower sideband. So in this case, if you see from here, the bandwidth becomes smaller. Okay, bandwidth becomes FM, half of it, half of the double sideband full carriers. Yeah. So bandwidthnya menjadi separuh. Okay, bandwidth becomes FM. Okay. So this is a single sideband without carrier. Okay, single sideband without carrier. So this is using the upper sideband. Okay, this is a USB. Okay, there's no carrier, there's no lower sideband in this case. So this is a FC, this is the LSB. Okay. So you see that from here we only have single sideband without carrier. There's no carrier component. The carrier component has been suppressed completely, and the lower sideband has been removed using the filter. Okay, menggunakan filter, so kita boleh remove salah satu sideband. We can choose either one sideband using the filter component. If we use filter, we can remove the sideband. Okay, and also we can also remove the carrier. Okay, there are a few methods to remove the carrier component and also the sideband component. Okay, either we want to use a filter method or we want to use a phasing method. Itu nanti kita akan lihat. So in this case, if you see here, the bandwidth, okay, the bandwidth is still the distance from the carrier to the upper sideband. In this case, the bandwidth is equal to FM. Okay, so bandwidth for the single sideband with carrier and bandwidth for the single sideband without carrier, the bandwidth is still the same, which is equal to FM, frequency of the input message. Okay, so ini is actually you have the imaginary line. For example, seolah-olah macam you ada imaginary line. So the bandwidth is actually just half of it, half of the double sideband full carrier, which is equal to FM. Example 2.9. Okay, example 2.9. Okay, the last example. For 100 watt of total available power in the sidebands, compare the power in the sideband when the modulation standard AM 100% versus a suppressed carrier where 90% of the carrier is suppressed. The second question say that how many times greater the sideband power in the suppressed carrier case. So this example is quite confusing actually. So in the first question, it said that during the 100%, we need to compare between 100% and so initially we have the 100%. We have 100% of double sideband full carrier, and then we have another one is a suppressed carrier where 90% of the carrier from the double sideband full carrier is suppressed. Okay, so mula-mula we have the double sideband full carrier, okay, with M equal to 100%, and then we suppress the carrier. Okay, we suppress the carrier for 90%. That means the remaining carrier becomes 10%. Okay, and we have the upper and lower sideband. Remember previously, when we suppress the carrier, theoretically we increase the sideband amplitude. Okay, theoretically, when we suppress the carrier, it looks as if some of the portion of the carrier goes to the sidebands. Seolah-olah portion suppress itu pergi kepada sideband. Okay, ini secara theoretical. Macam kita lihat tadi, dia punya amplitude becomes a VMVC over 2 when we suppress completely. So here you see from this, for the first scenario, if m equal to 1, we can calculate the carrier power. So this is supposed to be small c, PC. Power carrier becomes 2 over 3 of the total power. So 66.7 from the total 100 watt. Total is given 100 watt. Okay, so PC is equal to 66.7. So based on power calculation, m equal to 1. Okay, m equal to 1, that means power carrier is 2 over 3 of the total power. So PC is 66.7 and the remaining is for the both sideband, which is 33.3 watt. Okay, so this is 66 watt, 66 watt, this is 33 watt. Okay, sorry, for both of this is 33.33 watt. Okay, so now when we want to change to suppress carrier, what happened is that 90% of the carrier is suppressed. So 90% from the original carrier from here is suppressed. So 90% contributes 60 watt. Okay, this 60 watt is suppressed from the carrier, and from this slide, theoretically it goes to the sidebands. Okay, dalam case ini, dalam you punya slide, apabila kita suppress the carrier, the power goes to the sideband. Dia pergi kepada sideband. Macam mana boleh jadi seperti itu? This is just a theoretical concept. Okay, so you see that the 90% suppression from the carrier go to the sideband. Okay, that means the new sideband power becomes 33.3 plus 60. This is 90% suppression from the carrier. Apabila kita kurangkan 60 watt daripada carrier, we move it to the sidebands. So therefore, the new sideband power becomes 93.3. So 60 plus 33.3. So both of these now, okay, is 93.3 watt. Okay, so the power ratio, okay, the power ratio of the, okay, so the next question asks how many times greater is the sideband power in the suppressed carrier compared to the double sideband full carrier. So when we want to compare, you need to divide the power ratio. So power sideband new, after we sum with the 90% of the carrier suppression, and then we divide with the power sideband old, previously is 33.3. So this is 93.3 divide with 33.3. Okay, this is a new, this is a old. Okay, power sideband yang sebelumnya dalam double sideband full carrier adalah 33.3. The power sideband of the new power sideband in the suppressed carrier is 93.3 after the suppression. So when you divide this one, you get 2.8. 2.8 we can calculate in terms of decibel. Okay, so remember this is a power ratio, there's no unit. Okay, so when you convert into decibel, 10 log 2.8, you get 4.5 dB. Okay, that means in AM, information is only 33.3. This is during the ideal case. Okay, 33.3 percent, because our total power is 100 watt. So 33.3 watt out of 100 watt is 33.3%. But in double sideband suppressed carrier, the power is 93.3%, which is higher. Okay, So itu secara teoreticalnya apabila when we suppress the carrier, it goes to the sidebands. That one is a theoretical concept. Example 2.10 is similar with example 2.9. So this is quite confusing. You can read on your own. Personally, this example will make the students confused. So I don't want to go very detailed, so that I hope you understand the concept is that in this slide, when we suppress the carrier, the power goes to the sidebands. Okay, that's a theoretical concept. Macam mana nak buat secara practical, that one is another issue. Okay, so how can you suppress the carrier and you give to the sideband? So that one is like a theoretical, this one is a theoretical concept, but we need, when you do the practical thing, that one is need to think about how the circuits works. And advantage of the single sideband, any loss, advantage of power conservations, because there's no carrier power, there's no sideband power, we only use a single sideband. Bandwidth conservation, bandwidth is equal to Fm, which is we managed to reduce the bandwidth. Less fading. Fading means multiple attenuation. Okay, berlakunya proses attenuation yang berulang-ulang. Okay, multiple times of attenuations. Attenuation that happens many times. Noise reduction, of course. Noise reduction, remember Pn is equal to KTB. Okay, if we reduce the bandwidth, that means we can reduce the noise power. And in terms of circuitry, the circuit is complex and it requires a difficult tuning concept. Okay, last for the ini mungkin saya akan terangkan next week lah. Double sideband VSB. So double sideband vestigial sideband. This one is for the TV broadcasting. So I just simply want to show you this one. So for the vestigial sideband, you see that PLSB is not equal to the PUSB. Okay, dari segi amplitude dia berbeza, and in terms of bandwidth also different. Okay, because the bigger bandwidth is for the video signal, the smaller bandwidth is for the audio signal. Okay, so that one is the vestigial sideband AM. Okay, so itu sahaja for today. So I will for next. So now is for the attendance. Sorry for that. So attendance, you can prepare your. You can turn on your QR code scanner. So if you already scan the attendance, you can go home. You can go to another class. Okay, you can go to another class. Yeah. Okay, saya buat balik. I don't know why it is like this, so harap sabar sekejap.
Doctor,
Yeah.
hello.
Yeah.
Yeah, while waiting, I just want to double check on the project.
Okay.
So my team is doing the amplitude modulation, and I
Okay.
wanted to ask about the proposed system design.
Okay.
So right now, our team, we have just a rough look of how our GUI looks like, but it does not interact with one another yet. So right now, we just have like the basic things like the frequency, sampling frequency, carrier frequency, and so on. So maybe in the future, I'll add in like maybe a plot,
Okay.
a period plot inside. But I just wanted to double confirm with you. So it's okay if right now for the proposal video that we have just a GUI, just the rough look of how our GUI looks like, but it does not function yet. Is that
Yeah.
okay?
Yeah, that one is okay. No problem.
Yeah. All right. Thank you.
So saya tak boleh nak open sekejap I'm sorry for the delay. Okay. So if you have other question, you can ask me now. No problem. Siapa yang dah ambil attendance boleh boleh pergi ke kelas lain Sorry for the delay.
Thank you, Doctor.
Okay.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doktor.
Welcome.
Doktor nak tanya,
Ya, boleh. Silakan.
untuk block diagram tu, kita
Okay.
kena buat ke?
Kena buat ke? Maksudnya you nak
Maksud
gantikan
saya
dengan benda lain
block diagram dengan apa tu, sistem design tu,
Okay.
dia salah satu je kan?
Yalah, sistem design tu kita mungkin tak nampak macam mana bentuk keseluruhan sistem. So block diagram tu untuk membantu kita melihat apakah proses untuk kita membuat sistem tu lah sebenarnya. The process the block diagram consists of some parts of the overall system. So adakah you nak gantikan dengan benda lain, contohnya you nak buat dalam bentuk lakaran ke, lukisan ke? You nak buat dalam bentuk lakaran, for example. Is it?
Kalau macam flowchart tu bukan
Flowchart tu lebih kepada proses.
Oh, okay.
Macam mana nak buat step 1, step 2, step 3. Block diagram yang saya maksudkan adalah block by block of the overall system.
Oh, okay.
So yelah, you punya sistem tu ada apa sebenarnya ada block ini, block ni. So dia bersambung dia connected to one another. So you have the input block, you have the system block, you have the output block, for example. So macam mana result blocknya macam mana, macam itulah. So punya gambaran dia macam mana. Flowchart tu lebih kepada proses. First you need to do this, next you need to do this, next macam tu.
Okay, Doktor. Thank you, Doktor.
Okay, welcome. Siapa lagi belum ambil attendance?
Lepas tu, Doktor, yang
ya.
filler table tu,
Okay.
yang filler table tu dia nak setiap ahli satu ke macam mana?
Tidak. Saya
Satu group
cadangkan, saya cadang you kena ada lebih daripada 3 lah.
Oh, okay.
Filler table is your planning. Dia adalah planning. Macam mana kita nak menyelesaikan isu yang kita akan hadapi nanti. How to solve the issue, what to do. So filler need to be, dia perlu dibuat pada peringkat awal kerana dia adalah planning kita. Macam mana kita nak solve beberapa isu yang berbangkit nanti. So it's not a one member one.